notes are about a special type of sequence known as an arithmetic sequence. First, take a look at that word arithmetic. It looks like the word arithmetic, doesn't it? But arithmetic is an adjective and arithmetic is a noun. So arithmetic in this sense is describing the type of sequence. Now, what type of sequences are arithmetic? Those are sequences that require the addition or subtraction of the same number over and over again to get the next term and the next term and the next term. This number is known as the common difference, D. In this example, 5, 8, 11, 14, notice that we're always adding 3 to get from one term to the next. Therefore, our common difference, D, is equal to 3. If we had been subtracting 3, our difference would just be negative 3. So in this video, we're going to talk about some characteristics of arithmetic sequences, and we'll learn how we can write explicit and recursive rules for them, as well as other problems you might see involving arithmetic sequences. So let's try to generate a rule for this arithmetic sequence, and to do that, I'm going to rewrite our terms in a very interesting way. 5 I'll leave alone, but 8, I'm going to call that 5 plus 3, because isn't that how we got the 8? We just took our common difference and added 3 to 5. How do I get 11? Well, I took our 5 plus 3 and I added 3 on again. How did I get 14? Well, I took our 11 and I added 3 on one more time. So instead of 5, 8, 11, 14, I wrote 5, 5 plus 3, 5 plus 3 plus 3, and 5 plus 3 plus 3 plus 3. I did that so we could hopefully see a pattern. Notice how many times we added 3 on. I added 3 on 0 times. I added 3 on 1 time. I added 3 on twice. And then I added 3 on 3 times. Also, remember that this was our first term, this is our second term, this is our third term, and this is our fourth term. In general, if I want to get our nth term, does it make sense that we would take 5 and add on 3 n minus 1 times? Let's make sure that makes sense. To get the third term, we added 3 on twice. We added it on to 5. To get the fourth term, we added 3 on 3 times. 4 minus 1 is 3. 3 minus 1 is 2. 2 minus 1 is 1. You can see that the number of times we're adding on our common difference to get to the nth term is n minus 1. So we can say that an, in this case, for this sequence, I'll write it over here, is equal to 5 plus our common difference, 3, times n minus 1. I know our common difference was 3, but what's the 5? Well, 5 is just our starting term, a1. Any arithmetic sequence can be written this way. Let's see if we can write a recursive rule. I know that to get our nth term, we're taking our previous term and adding 3. That's it. That's our recursion. Except remember, we always have to say where to start in order to generate our sequence. So in red at the bottom, we have our recursive rule, and in black at the top, we have our explicit rule. Let's generalize this for any arithmetic sequence. In general, for an arithmetic sequence, our nth term is going to be our first term, a1, plus d n minus 1 times. The pattern that we saw on the first slide hopefully explains this. You're starting with your first term and adding on your common difference n minus 1 times. That's our explicit rule. Very handy. A recursive rule will always be to get your nth term, take your n minus first term, and add d. And then we need to say whatever a1 equals. I don't know what it is, so I'm just going to call it a1. So notice for arithmetic sequences, we have these really nice patterns. We can always find an explicit or a recursive rule fairly easily if our pattern is just always adding or always subtracting. Let's take a look at an example using what we just talked about. Let's find an explicit and a recursive rule for this sequence. First thing we want to do is find D. Notice each time we are subtracting 2. Therefore, D is -2. The other ingredient that we need to write our explicit rule is A1. A1, I can just look in this case and see that A1 is 12. So for our explicit rule, I can see that our nth term will be our first term, 12, plus -2 n minus 1 times. Now, plus a negative, that's just subtraction. It's fine to leave it in this form, but I know that I might have to do something with this. If I have to, I don't know, maybe plug in a little bit later, it might be nice to have this in a little bit more simplified form. So what you can do, if you wish, is distribute that -2 and combine like terms. an equals -2n plus 14. I like it when it's simplified sometimes, because now if I have to plug in, it's pretty easy. Just -2 times a number plus 14. Let's get our recursive rule. Well, that one's not so bad. I know to get the nth term, I just take our previous term and subtract 2. And we would start at 12. So we found our explicit rule by using the pattern we discovered, or the general formula, and then I simplified. For our recursive rule, all we're doing is taking the previous term and subtracting 2, and A1 is 12. Let's continue with the same sequence. This is the same sequence that we saw on the previous page, 12, 10, 8, 6, etc. In fact, I'm going to remind ourselves that our explicit formula was -2n plus 14. That's the simplified one. Let's see, find A13. Well, I have our rule for the nth term up in the top right. A13 is -2 times 13 plus 14, just by plugging in. -26 plus 14, that's just -12. Having our explicit rule is really nice, because I can find any term value I want just by plugging in. Let's see if we can go the other way. A certain term value is -84. What is its term number? Well, if an is -84, but I don't know what n is, I can still plug in. We're just plugging in for an instead of for n. And now I can solve. We can subtract 14 from each side, and we get -98 equals -2n. Now I can just divide both sides by -2, and I get n equals 49. So its term number is 49. Or I can say the 49th term is -84. Think about what kind of number n has to be. N is our term counters, or our term number. So n can't be a number like 2.5. You can't have the 2.5 term. That doesn't make sense. N has to really be a natural number in this case. So if I'm solving and I get something negative or something that's not a natural number, I know something has to be wrong. So this is an example of how we would use our explicit formula to answer certain questions. Let's end with one last example. Let's suppose we know the 5th term of an arithmetic sequence is 10, and we know the 11th term from the same arithmetic sequence, and that's 34. Find the common difference and the first term. Let's use our math sequence notation to write out what we know. The 5th term is 10. The 11th term is 34. I just used math to write down the sentences that were given. How could we find the common difference first? Well, to go from the 5th term to the 11th term, think about how many spaces we jumped. I can almost kind of picture this. 5, or maybe 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I'm kind of creating a space to write in all the terms. So 1, 2, 3, 4. On our fifth term, we had the number 10. 6, 7, 8, 9, 10. 11th term, we had the number 34. How many spaces did we jump to get to 11 from 5? We jumped 6 spaces. And how far numerically did we go from 10 to 34? We went up 24. It should make sense then that our common difference is 24 over 6. I jumped up 24 numbers, and that represented a jump of 6 terms. So I must have jumped up 4 numbers to get to the next term, to get to each one. We essentially found a sort of average here. Makes sense. So D is 4. To go all the way from 5 at the 5th term to the 11th term, we must have jumped 4 6 times because we jumped 24 total. So I found D. D is 4. How do we then get A1? Well, there's a couple of ways of doing it. You might just want to think backwards and say, okay, if we're adding 4, then to go backwards, I have to keep subtracting 4. Or you could think about plugging in. I know that our explicit form has to look something like AN equals A1 plus D n minus 1. But notice, I know D. I have one of our unknowns. Do I know a specific n and an I can plug in? Sure, I know that A5 equals 10. Let's plug in 10 for A5. So now I have 10 equals A1 plus 4 times 5 minus 1, because that is A5. So I'm using a specific term value and term number that I know to help solve for A1. Now I know that 10 equals A1 plus 4 times 4, just by simplifying the 5 minus 1 in the parentheses. So if 16 plus A1 equals 10, I know that A1 equals negative 6. So I used the formula we know. I found D over here, so I can circle that. I used the formula that we knew, and I found D by thinking about how many jumps we made. And then I plugged in and was able to solve for A1. And I could have also worked backwards, but just in case that A5 was actually a A100, and I didn't want to have to count backwards that many times, it's nice to have a formula to rely on. And that's the really nice thing about arithmetic sequences, is that we always do have that formula, and it's a pretty nice, consistent pattern. Good luck!